300 miles off the coast of Oregon, nearly a mile beneath the surface of the Pacific, the ground itself is rising. Not slowly. In the way continents drift, measurably. Daily. A patch of ocean floor the size of a small city has been swelling upward for years now, inch by inch, pushed from below by a reservoir of molten rock that scientists can track in real time, but have never once laid eyes on. Every day, more than 140 instruments, wired into 660 miles of fiber optic cable running along the seafloor, send a stream of data back to laboratories on land, pressure readings, seismic tremors. The barest fractions of an inch of ground swelling upward against the crushing weight of the ocean above it. And every day, the answer to the only question anyone actually wants answered stays exactly the same. Has it erupted yet? No, not yet. That headline promised you a volcano erupting right now, somewhere beneath the waves, hidden from view. That's not quite accurate, and it's worth being honest about the difference. Because the true story is stranger and more suspenseful than the headline lets on. Axial seamount. The volcano the story is about has not erupted. It is doing something arguably more remarkable. It is standing on the edge of eruption, in plain sight of the most sophisticated ocean monitoring network ever built, and scientists still cannot tell you the day it will finally go. Not because they aren't watching closely enough, because the one thing that matters most, what the magma is actually doing right now in the chamber. Beneath the seafloor is something no instrument on Earth can directly see. We have built an extraordinary nervous system wired into the ocean floor, and it still cannot show us the heart it's monitoring. To understand why this particular mountain has become one of the most closely watched objects on the planet, you first have to understand what it actually is and where it sits. Axial seamount rises more than 1,000 feet from the surrounding seafloor, a genuine mountain, taller than many volcanoes you'd recognize on land, except its summit still sits roughly a mile beneath the waves, deep enough that sunlight never reaches it. Deep enough that the water pressure alone would crush an unprotected human body instantly. It sits directly on top of the Juan de Fuca Ridge, one of the seams in the Earth's crust, where two tectonic plates are slowly pulling apart from each other, dragging the ocean floor open like a wound that never fully heals. Magma rises to fill that gap continuously, welling up from deep within the Earth's mantle. And Axial happens to sit at one of the most active, most magma-rich points along that entire boundary. It is, by a wide margin, the most active submarine volcano yet identified in the northeastern Pacific, a title it has earned through a documented eruption history stretching back centuries, with confirmed eruptions in 1998, 2011, and 2015, and geological evidence suggesting roughly 50 eruptions over the past 800 years alone. That 2015 eruption is the reason we're able to have this conversation with any confidence at all. In the months before it happened, scientists monitoring Axial noticed the seafloor rising and the rate of small earthquakes climbing. And a team led by geophysicist Bill Chadwick of Oregon State University's Hatfield Marine Science Center made a call that few volcanologists would ever dare make in public. They predicted, with a specific window of time, that axial seamount was going to erupt. It did. It remains one of the only successful advanced forecasts of a volcanic eruption in recorded scientific history. Not a vague warning that something might eventually happen, but an actual dated prediction that came true. That success turned Axial into something rare in volcanology. A natural laboratory scientist could use not just to study a volcano after the fact, but to test whether an eruption could genuinely be seen coming. The instrument responsible for most of what we now know about Axial's inner rhythms is a network with a name that undersells its ambition. The Ocean Observatory's Initiative's Regional Cabled Array, built and operated by the University of Washington with funding from the National Science Foundation. Laying 660 miles of fiber optic and power cable across the seafloor of the northeastern Pacific was by itself an engineering undertaking on the scale of a small national infrastructure project. Cable ships spent years spooling line across canyons, ridges, and abyssal plains, connecting shore stations in Oregon and Washington to a scattered constellation of seafloor instrument nodes, clustered directly around Axial's summit and caldera rim. Each node hosts a small suite of devices, bottom pressure sensors sensitive enough to detect ground movement of a few millimeters, seismometers listening for the countless tiny cracking sounds of rock breaking under stress, hydrophones tuned to the acoustic signature of magma moving underground, and cameras that, on the rare occasions there's anything worth pointing them at, can transmit live video back to shore in real time. It is, without much exaggeration, the closest thing science has ever built to a permanent, wired nervous system draped across an active volcano. And it still, after everything, cannot see the one thing that would actually answer the question everyone keeps asking. That's the paradox we're sitting with for a moment. An instrument this sophisticated, this comprehensive, still cannot look inside the mountain. Every sensor in the regional researchers openly discussed a plausible eruption sometime in 2025. Then, in one of the more humbling moments in recent volcanology, the mountain simply slowed down. Inflation rates that had been climbing steadily through 2024 began to taper through 2025. And the earthquake activity that typically accompanies rising magma never built to the intensity researchers expected. By the fall of 2025, Chadwick and his research partner Scott Nooner were forced to revise their own forecast publicly, extending the window into mid-to-late 2026 and cautioning in their own words that nothing appeared imminent. It is not the first time Axial has done this. Each of its recent eruptions has apparently required slightly more inflation than the one before it to finally trigger. A pattern researchers believe mirrors the behavior of Krafla, a well-studied volcano in Iceland, where each eruption seems to compress and stiffen the surrounding crust just enough to raise the bar for the next one. As of the most recent reporting, the ground at Axial's summit sits about 4 inches higher than it stood in the moments before the 2015 eruption, with researchers estimating it likely needs to climb roughly 8 more inches before conditions favor another eruption, whether that happens in the coming weeks, the coming months, or drags on well past this year. Nobody currently monitoring the volcano is willing to promise. This is where the second half of the headline finally earns its place. Because even with all of that data streaming back to shore every 15 minutes, scientists genuinely cannot see what's happening beneath the seafloor in any sense a human being would recognize as seeing. No camera, no diver, no submersible has ever peered directly into an active magma chamber and watched molten rock behave the way you'd watch weather roll across a valley. What researchers actually have is indirect evidence, translated through instruments, inferred rather than witnessed, pressure sensors on the seafloor that detect the ground itself, rising and falling by fractions of an inch, seismometers that register the countless tiny earthquakes caused by rock cracking as magma forces its way upward, and years of pattern matching against the mountain's own history, treating each prior eruption as a kind of imperfect answer key for the next one. That is the entire toolkit. There is no direct window into the magma chamber itself, no way to look inside the earth and watch the molten rock accumulating, shifting, deciding, in whatever sense magma can be said to decide, that it is finally ready to break through. It helps at this point to understand exactly why the deep ocean resists observation so completely, because it isn't simply a matter of visibility. At a mile down, sunlight has long since been absorbed and scattered away by the water above, leaving permanent, absolute darkness. No daylight ever reaches Axial's summit, not even a trace of it at any hour of any day. The pressure at that depth is roughly 150 times what you feel at sea level, enough to crush an ordinary submarine hull, enough that every camera, every sensor, every piece of equipment lowered down to the seafloor has to be built, specifically to survive forces that would flatten almost anything designed for use in open air, even with cutting-edge sonar and remotely operated vehicles. Humanity has produced detailed maps of only a small fraction of the entire ocean floor. The deep sea remains, by a wide margin, the least explored environment on the surface of our own planet. Less thoroughly mapped in many places than the surface of the Moon or Mars, we have photographed nearly every square foot of rock and dust across 2 neighboring worlds, while entire mountain ranges sit unmapped in the darkness of our own oceans, 3 miles beneath ships that cross over them every day without anyone aboard knowing they're there. Submarine volcanism itself, as a category of geological activity, remains almost entirely hidden from us for exactly these reasons, and the scale of that blind spot is worth sitting with. The overwhelming majority of all volcanic activity on planet Earth, by most estimates somewhere around 3/4 of it, happens not on land where we can see the smoke and feel the tremors and evacuate the towns nearby, but beneath the ocean, along mid-ocean ridges just like the one Axial sits on. Entirely out of view, mostly unmonitored, mostly unknown. Every year, new crust is created along these ridges as magma wells up and hardens into fresh seafloor. An enormous, continuous process of planetary renewal that almost no human being will ever witness directly, because it happens in crushing pressure and absolute darkness, thousands of feet beneath ships and storms and everyday human awareness. There is life down there too, thriving in conditions that would kill almost anything else on Earth. Axials. Caldera happens to host some of the most intensely studied hydrothermal vent communities in the world. Where seawater seeps down into cracks in the fresh volcanic rock, it gets superheated by the same magma driving the inflation cycle, dissolves minerals out of the surrounding basalt, and comes roaring back out of the seafloor through chimney-like vents that can reach temperatures exceeding 600 degrees. Hot Fahrenheit water that would flash boil instantly if it weren't held liquid by the crushing pressure of the ocean above it. Around those scalding vents in total darkness, entire ecosystems have evolved that don't depend on sunlight or photosynthesis at all, but on cheosynthesis. Bacteria that harvests energy directly from the chemicals dissolved in the vent fluid, forming the base of a food web that supports dense colonies of tube worms, blind shrimp, and pale crabs clustered around plumes of mineral-rich water in numbers that can look on camera almost impossibly crowded for an environment this hostile. When Axial erupts, fresh lava can bury entire vent communities in a matter of hours, and yet within months, sometimes even weeks, new vents typically form nearby in the same eerie, thriving ecosystem reestablishes itself on the freshly cooled rock, one of the clearest demonstrations biologists have ever documented of how quickly life can recolonize ground that was, geologically speaking, born only moments before. That invisibility doesn't mean submarine eruptions never get caught in the act. It just means catching one requires a rare, precise alignment of scientific readiness and outright luck. In April of 2025, researchers aboard the deep-sea submersible Alvin, operated by the Woods Hole Oceanographic Institution, achieved something volcanologists had spent years hoping for. They arrived at a stretch of the East Pacific Rise, another mid-ocean ridge system, at almost exactly the moment an eruption began, and watched it happen through the submersible's viewports. It was the culmination of nearly a decade of patient monitoring at that particular site, waiting for exactly the right seismic signs to justify sending a crewed vehicle down at exactly the right time. Moments like that remain vanishingly rare, not because submarine eruptions themselves are rare. They are, if anything, it's the single most common type of volcanic event on the planet, but because witnessing one in person requires threading an almost impossibly narrow needle of prediction, timing, and deep-sea logistics. Alvin itself carries a kind of institutional weight in ocean science that makes its presence at that eruption feel less like coincidence and more like inevitability. Commissioned in 1964, the submersible has spent more than 6 decades as one of the most productive research vehicles ever built. Credited with helping researchers first document hydrothermal vents and their strange sunlight-free ecosystems back in the 1970s, and later famously used to locate and photograph the wreck of the Titanic in 1986, it has been rebuilt and upgraded, piece by piece over the decades, to the point where very little of the original 1964 vehicle remains, and it continues to serve as one of only a handful of crewed submersibles on Earth capable of carrying scientists safely to depths where an active volcanic eruption might actually be witnessed firsthand. Every dive Alvin makes to a site like the East Pacific Rise carries genuine risk, real cost, and a payload of scientific instruments calibrated for exactly the kind of narrow window of opportunity that a live eruption represents, which is part of why no crewed vehicle has ever been sent down to watch Axial itself erupt in real time. The risk to reward calculation simply hasn't favored it, not when robotic vehicles and permanent seafloor cables can gather most of the same data without placing a human crew directly above an active vent field during an actual eruption. None of that is expected at Axial seamount, and it's worth being direct about that. because these documentaries have a habit of letting scale bleed into danger where none exists. Unlike Hunga, unlike Kikemgeni, Axial sits nearly a mile beneath the surface, isolated by hundreds of miles of open ocean from the nearest populated coastline, and its eruptions produce slow-moving lava flows rather than explosive blasts, a fundamentally different, gentler style of volcanism driven by the specific chemistry of its magma and the crushing water pressure that suppresses the kind of violent gas expansion responsible for events like Hunga, Tonga. When Axial last erupted in 2015, researchers monitoring the site recorded the seafloor at the center of its caldera dropping by roughly 8 feet in a matter of hours. As the magma chamber beneath it partially drained and the ground above it collapsed inward to fill the space, dramatic, geologically speaking, and entirely undetectable to anyone standing on the Oregon coastline 300 miles away. Lava spread across the seafloor, cooled almost instantly in the frigid deep ocean. Water and reshaped a portion of the caldera floor in ways that follow-up robotic surveys were able to map in careful detail afterward. No tsunami, no earthquake felt on land. No headline urgency of the kind the framing scientists can't see what's below seems to promise. Just a mountain, doing what mountains like it have done roughly 50 times in the past 8 centuries, entirely out of view, exactly as expected. The word gentler deserves a bit of unpacking, because the physics behind it are genuinely strange. On land, an erupting volcano releases pressure violently, in part because dissolved gases inside the rising magma, mostly water vapor and carbon dioxide, expand explosively as the magma nears the surface. The same way a shaken soda can erupts the instant the pressure holding it closed is released. At the surface, that expansion happens against ordinary atmospheric pressure, offering the gas plenty of room to violently unclench. A mile beneath the ocean, the physics change completely. The water column above Axial's summit exerts roughly 150 times the pressure found at sea level, and that immense weight suppresses the same gas expansion that makes land eruptions so explosive, holding the dissolved gases in solution far longer and forcing the magma to escape more like a slow-moving flood than a detonation. The lava that eventually reaches the seafloor at Axial doesn't erupt so much as ooze, spreading in thin, glassy sheets and bulbous, pillow-shaped lobes that form almost instantly as scorching molten rock meets water only a few degrees above freezing, a violent temperature collision. Thousands of degrees Fahrenheit meeting near-freezing seawater in an instant. That produces one of the most recognizable textures in all of marine geology. Pillow. Basalt, stacked and rounded. Elephant hide mounds that blanket entire sections of the caldera floor after every eruption. A permanent record etched directly into the rock of exactly how the lava moved before it froze solid. After the 2015 eruption cooled and hardened into that landscape, scientists didn't simply wait for the next inflation cycle to begin. They sent robots down to read the wreckage. Autonomous underwater vehicles, essentially self-piloting submarine drones equipped with sonar and high-resolution cameras, spent days methodically combing the caldera floor, building detailed 3-dimensional maps of the fresh lava flows meter by meter. Those surveys let researchers measure, with genuine precision, exactly how much new rock the eruption had produced, exactly where the flows had traveled, and exactly how the caldera floor's shape had changed as a result. Data that becomes the baseline for measuring every subsequent year of inflation leading toward the next eruption. It's a strange kind of forensic science, performed not in the aftermath of a crime, but in the aftermath of a birth. Cataloging. With total precision, ground that didn't exist a few weeks earlier, formed entirely out of view, entirely without witnesses. Confirmed only once the robots finally arrived to measure what the volcano had quietly built. Other submarine volcanoes around the world offer their own strange proof of how much happens beneath the waves without any of us noticing. In the southwestern Pacific, a shallow volcano nicknamed Cavachi, known locally as Cavachi's Oven, has erupted roughly 20 times in the historical record, repeatedly building small islands of cooled lava that rise briefly above the waves before the ocean tears them back down again within months. In 2022, satellite imagery revealed something almost too strange to be real: sharks, apparently unbothered, swimming inside the volcano's active acidic crater, a discovery that earned Cavachi its inevitable nickname among ocean scientists, Volcano, near Grenada in the Caribbean. Another active submarine volcano called Kik Imjeni sits close enough to the surface and erupts often enough that a permanent exclusion zone has been maintained around it since 2001 because a large enough eruption there could reduce the density of the surrounding water so sharply that ships passing overhead could genuinely lose buoyancy and sink. And in January of 2022, a volcano called Hunga in the South Pacific produced what remains the largest atmospheric explosion ever recorded by modern instruments. A submarine eruption so violent it sent a shockwave circling the entire planet multiple times, launched a plume of water vapor higher into the atmosphere than any eruption in the satellite era, and demonstrated in the most dramatic terms possible just how much destructive force can build in complete secrecy beneath the surface of the ocean before the world ever notices. And yet the fact that nothing dangerous is likely to happen doesn't make the waiting any less remarkable, scientifically speaking. What's actually unfolding off the Oregon coast right now is one of the most ambitious real-time experiments in the entire history of volcanology. An attempt to answer a question that has frustrated geologists for as long as the science has existed. Can an eruption ever truly be forecast in advance, the way meteorologists forecast a storm, rather than merely explained afterward, the way historians explain a war, most of the volcanoes on land that threaten human lives? The honest answer remains no. Eruptions at Mount St. Helens, at Vesuvius, at nearly every volcano that has ever killed someone, have come with warning signs that were only fully understood in hindsight, patterns that made perfect sense the moment it was already too late to matter. Axial offers something different, a volcano so remote, so harmless to human life, and so thoroughly wired with instrumentation that scientists can afford to be wrong publicly, repeatedly, and learn from every failed prediction without anyone getting hurt in the process. Chadwick's team is now testing an entirely new approach, moving beyond the pattern matching that succeeded in 2015, toward physics-based models developed by researchers in Sweden and Switzerland, mathematical frameworks that attempt to simulate the actual mechanical stress building in the rock around the magma chamber. Rather than simply watching for the ground to reach a certain height and assuming history will repeat itself, if a model like that eventually succeeds where pattern matching has fallen short, it won't just solve the riddle of one remote seamount off the Oregon coast. It will hand volcanologists working on far more dangerous volcanoes, the ones sitting beneath cities and coastlines the whole world is watching, a genuine, physics-based method for finally answering the question that has always mattered more than any other in their field. Not simply whether a volcano will erupt, but when. So the story tonight isn't the story the headline promised. Nothing beneath the Pacific is currently erupting. No lava is currently spreading across a hidden caldera floor. No shockwave is currently racing toward any coastline. What's actually happening is quieter and, in its own way, more extraordinary. A mountain the size of a small city, sitting in absolute darkness beneath a mile of freezing water, slowly swelling with molten rock that no human eye has ever seen and no camera has ever captured. While more than 100 instruments strung along 600 miles of undersea cable measure its every breath in real time, waiting patiently for the moment its long, invisible inhale finally becomes an exhale. That moment is coming. Every scientist watching the data agrees on that much. What none of them can tell you, what no instrument on Earth can currently tell them, is exactly when. And so the mountain waits, and the cables keep transmitting, and somewhere beneath a stretch of ocean most of us will never see, in a place darker and more pressurized than almost anywhere else accessible to human instruments, the answer is already forming. We simply haven't found a way to read it yet.